Hello everyone, welcome back to the course on materials informatics. In this lecture we will talk about classification workflows. Just as a recap of what we did in the last lecture, we looked at a typical regression problem which is predicting median house prices in the state of California. We defined some performance metrics, root mean squared errors, mean absolute errors. And we also split the data into train and test sets, and in terms of splitting data we looked at random and stratified splits as well. We visualized the data, we understood correlations. There are some key variables or key features that were contributing more to the median house price than the other variables. So, understanding correlations is important. And then we prepared data for machine learning. Here we did a few things. So, we ensured that missing values were inserted. We used the median strategy for that, and then we converted text features into one hot encoded features, so numerical features, and then we also did standardization of all the feature values. And we also added new features, right. So, we did all those exercises using a bunch of transformers and pipelines, and then we fed the prepared data into different models. So, we looked at linear regression, we looked at decision tree, we looked at random forest, and we also looked at support vector machine regressions, right. So, we learned quite a bit of how to do machine learning, at least with the classical sort of quote unquote simpler models. In this lecture we will basically do classification. So, we will go through a similar workflow as we did in the case of regression. So, there will be some slides where I will explain some concepts, and then we will go to a notebook to look at how the code is actually evaluated. And as mentioned before, the schematics, unless otherwise mentioned, I have taken it from this textbook by Aurélien Geron. Okay. Just to recap some of the important functions or classes that we used in our regression exercise. We will use some of these but not all of these, but this is a good list to have and use it as a reference. So, the first relates to how do you get data and then visualize the data. So, we typically want to deal with pandas data frames. These are really nice sort of data objects to handle especially large amounts of diverse data. And you can read typical sort of CSV files, right. So, if you are familiar with dealing with Excel sheets, you can always export data from your Excel sheets into CSV files, and then you can read within pandas, right, directly from CSV files. And another sort of useful library that or useful library to get familiar with is matplotlib, because this is the library that we often use for plotting in Python. Pandas has some simple plotting routines within itself, but matplotlib is more powerful. You can generate more intuitive, more complicated plots, right. And we also use this ready made function called train test split from scikit-learn. So, sklearn is the sort of module or package that we use quite often, especially with classical machine learning within Python. So, within scikit-learn there is a ready made function called train test split, and then we also, so train test split by default does the split randomly. We also looked at stratified shuffle split, and then in order to look at correlations within the data, this is why loading your data as a data frame is useful, because there is a ready made function called cor, right. So, that already gives you what kind of correlations exist between amongst features or amongst your feature and your target variable, right. And we also did a lot of data cleanup. So, the first thing we did was inserting missing values. Once again we use this class called simple imputer, which has a fit function and a transform function, and you can use that to put in missing numerical values in your data frame. We also use this one hot encoder class from scikit-learn preprocessing package, which has a fit underscore transform function. And then the standardization we performed using standard scalar class, which is also under scikit-learn preprocessing, right, and this also has a fit and a transform. So, you need to get for standardization you need the mean and the standard deviation. So, the fit gives you the mean and standard deviation, and the transform actually changes your data, rescales your data. And for any model, any machine learning model that you have with scikit-learn, in order to create that model or fit that model, you simply use the fit function. And the fit function typically takes 2 arguments. One is your set of features, so this is usually an array or a matrix, and y is your set of targets, usually a vector, right. And if you want to make predictions either on the test data, or if you want to look at how the model is learning within your training data itself, then we use the predict function. So the predict function just takes 1 argument, which is your features. So for the set of features you want to make a prediction. And then in terms of metrics for regression, we looked at mean squared error and mean absolute error. These are again ready-made functions available within scikit-learn metrics. For performing cross validation, there is a different package called module selection within scikit-learn, from where you can take in cross validation scores, or we can use this function to calculate cross validation scores, and this function is quite flexible, so you can do multiple k-fold cross validation. And finally we also looked at grid search cross validation. This is a very systematic way to optimize hyperparameters, and is very commonly used both in regression and in classification models. And in order to use grid search cross validation, we used this model selection package again. Once again, this is just a recap of all the functions we used. This is a good reference to have, because whenever you are going through a machine learning workflow, you will probably have to deal with some of these functions. But for the classification task, we will take a slightly different approach. We will use much simpler functions, and we will use a slightly different approach of fitting models, right? But this is a useful reference to have. Okay. So how is a classical classification workflow compared to regression? The workflow is actually quite similar. So first of all, you frame the problem just like we did in our regression exercise. We wanted to predict housing prices, so similarly you frame the problem here, and then second almost always is getting the data, and the third is we want to visualize the data, understand how the data looks like, understand some of the features associated with that data, and then we have to do some preparation, pre-processing, right. So that could be cleanup, standardization and so on. And then finally you select a model and then you train a model. You basically use the fit function, and then you fine tune your model. So you optimize the hyperparameters associated with that model, either using grid search cross validation or randomized cross validation, randomized search cross validation. And then the final step is almost always to present or deploy your final model. So presenting the final model would be evaluating the model on a test set that the model has not seen at all, and reporting how the model is performing in that test set. Deployment can take again multiple forms, that ranging from a simple scientific publication all the way to deployment in an industry setting, right. Okay. So what is the problem we will take for our classification workflow? The problem is as follows. So we want to classify handwritten digits from this database called MNIST. So MNIST is a very nice database. It has a lot of graphical content. So think of this as your old fashioned CAPTCHA, right. So if you were to sign on to new websites, you will often be asked to decode letters, right. Letters or alphabets within a given plugin, and if you are able to classify it correctly, then you are assumed to be human, and then the website lets you in. So MNIST has collected such kind of human written digits which have been properly labeled. So for example, the first digit here is a 5 and it has been properly labeled as a 5 in the dataset. Second digit is 0, third digit is 4 and so on. So MNIST is basically a collection of well labeled data, often using CAPTCHA based collections. So it's a collection of well labeled data. And we will take the simpler case of one of the simplest databases, which has about 70,000 characters. So 70,000 numbers, all handwritten and all well labeled. So we can actually train a machine learning model to make predictions on on these human annotations basically. And it is also a very nice curated data set, because each character, so the 5 here for example, comes in a 28 by 28 pixel image. So 5 here is a 28 by 28 pixel image, 0 is a 28 by 28 pixel image and so on, right. So each character has a well defined size, and it is certainly a number. There are no text annotations here, so the data set is very clean. right, and also each picture itself, each picture of a digit itself is not colored, so it only has grayscale. So and in the typical way we sort of encode grayscale features or grayscale values in images is they have a value between 0 to 255, so 0 being fully opaque, so the pixel is completely opaque, and 255 being completely transparent, right. So so each pixel within this 28 by 28 pixel image just has a number assigned to it, which can be converted into a grayscale and can be visualized as an image. So this is a very nice, very easy to use data set for classification exercises. So we will be taking this data set, and our task is to once again classify these handwritten digits. So if we see a 5, we want to classify that as a 5, if we see a 6, we want to classify that as a 6, and so on. Okay. So what are the first steps, right? So first steps is of course getting the data. So I just showed a glimpse of the data, so let's get the data. We should also look at how to visualize individual images. So visualizing data is important. The nice thing once again about MNIST is that it's a nice data set. There is very little cleaning or preparation that we need to do, as we will see, but it's important to create a train test split, right. So we have 70,000 sort of characters, so maybe we will go 60,000 training, 10,000 split, 10,000 test kind of split. So let us execute these first steps by going to our notebook, right. So let us get to our notebook here. So as before, the first block of the code relates to ensuring that the version of Python is correct, is appropriate. We have the correct scikit-learn version. Import some useful packages such as NumPy, for example, and then also define some useful settings in our matplotlib so that our figures are pretty, and then we also define some paths where the figures can be stored, right. And then in terms of getting the data set itself, there is a very nice package within scikit-learn called datasets, which actually has a collection of openly available datasets that can be used for simple machine learning exercises. So the MNIST dataset that we want is actually already present in this scikit-learn datasets package. So from that package there is class called fetch underscore openml. Class or a function, I think it's a function called fetch underscore openml. So as long as we execute this function, so we specify what dataset we need, what version of it, and asFrame basically tells you whether you want the data itself as a data frame or just as an array. For simplicity we will just deal with arrays here, because our problem is quite simple. We don't need to go all the way to or complicate our problem by using pandas data frames, but you can replicate the same exercise using pandas data frames also. So there is no harm in doing data frames. I am just illustrating an alternative approach, right. So asFrame equals false basically tells you that we will import the data set just as an array, right. And then I am just displaying the kinds of values or kinds of or what does the data set actually contain. So the keys basically tells you something like column headings. So here you see that there is data, there is target, frame, categories, and so on, right. So target is basically the target value, so the number in the numerical form, right. So I have already executed blocks 1 and 2 because I wanted the data set to be available locally on my machine, but there are instances when the scikit-learn datasets package is not actually available. So the fetch underscore openml function fails at times due to internet connectivity, due to maintenance issues and the database and so on. In case if you try to execute this notebook and you tried executing the second block, the fetch underscore openml block, and it fails. So in case you have a failure, you can use this backup cell that I have written here. This basically directly fetches your MNIST dataset from a well-known sort of available website. It's basically from a GitHub repository, right. So instead of relying on scikit-learn's fetch underscore openml function, we can also get the dataset directly from a source. There are multiple sources available. This is one such source. So this code block basically defines that, right. So it defines from where you download the data, it writes a small fetch function, so that you can pass in the URL and then it will fetch the file for you. The file comes in the comes with an extension called .mat, and we need to ensure that we can convert the .mat files into NumPy arrays for our purposes, and for that we will use this library called SciPy. So from there we will use this function called loadmat. So the loadmat basically converts or helps you convert from your .mat format into a NumPy array. And once it is there in NumPy array, we can then define what are what data we actually need. So in this case I think we need mnist underscore data, which is our x variable, or basically our images, and mnist underscore label, which is our y variable or our features. So yeah. So and then there is some sort of shaping requirement that we need to do. So the data set comes in a different format if you download it directly. So that is what the last few lines do. So if so when you are trying to execute this notebook by yourself, if block 2 runs, do not execute block 3. So block 3 is a backup block. So if block 2 runs and you see this kind of an output dict underscore keys and it prints a bunch of keys, then you have downloaded that data set correctly and you can go ahead with executing the other blocks. So do not execute block 3 if block 2 runs fine, okay. And the nice thing about the other sort of to touch upon the final nice aspect about fetch underscore openml is that once you download the data directly from the scikit-learn datasets package, right, the data is already randomly shuffled. So you do not have sequential appearances of zeros followed by ones followed by twos and so on, all the numbers are jumbled, right. So splitting the data set into train and test splits are easy and so on. So it makes our training of our models very simple. Whereas if you download it from source, usually the data is very sequential. So the first, let us say the first 5000 pictures are all of zeros and the second 5000 pictures are all of ones and so on. Okay, so we have already executed the first 2 blocks. The data set is already available from fetch underscore openml. And then let us see if we have let us see what within the data itself, how is the data looking like. So we have defined 2 variables x and y here. X is our basically our set of images and y is our target, right. And if you look at your target, it is basically a single array, so of 70,000 numbers basically. So corresponding to each image x, there is a number associated with that. Let us now define a simple function for plotting any random image or any of the random digits, right. So here we are taking the 30,000th digit within our data set, right. And then in order to plot any of these digits, since these digits are very easy, they are grayscale quantities, there is a very simple matplotlib color map or color scheme called binary. So that is what is mentioned here, mpl.cm.binary. cm stands for color map and binary stands for whether it is 0 or 1. So you can use this color map and create very nice grayscale images. So basically when you download the data set comes in the form of a 28 by 28 pixeled kind of array, where each array has values between 0 to 255, right. So you can convert that into an image, grayscale image fairly easily with matplotlib, which is what matplotlib is doing here. So we see that the 30,000th image within our data set is actually a 3, right. Now let us see if so we visually see that the data set has a 3. Let us see if that is actually labeled as 3 in our target value, and turns out that it is actually labeled as 3. And the 3, so when we initially download the data set, the 3 appears as a text kind of label and not a numerical label, and for machine learning we need numerical labels, numerical targets. That is easier to handle. So the next block basically converts all of your target values into integers. So 3 in quotes in the previous cell now becomes just 3, so an integer. So I'm going to define a simple function called plot underscore digit. This function we can use later on, right, to plot any sort of random digit just to verify if you are training a model, if it's making predictions correctly to compare to what we expect. And then let's do a train test split. So unlike the regression exercise, when we tried to do random splitting of data set, stratified splitting of data set and so on, the fetch underscore openML already gives us very well shuffled data, and we are dealing with the classification problem where we are dealing with very standard images. So each image is only a 28 by 28 pixel image, each image is a grayscale image. So we do not have to do a lot of cleaning exercises before we have to create the train test split, right. So what we are going to do is do a very simple train test split. So we are going to take the first 60,000 data points of the data set as part of our training set, and then the remaining 10,000 we are going to keep it aside as our test set, right. Now this you can do only if your data set is very clean, right, and thankfully for us MNIST is a fairly clean data set. Okay, let's go back to our slides. Okay, the first task is to train what is referred to as a binary classifier, right. So what is a binary classifier? So let's say you see an image of a digit and you want to say whether it's a 5 or a not 5, right. I mean this 5 is an example. You can also say whether it's 1 or not 1, 0 or not 0 and so on. So you are basically trying to teach the model to say yes or no to a given question. So is the model seeing a 5? Then the answer should be yes or no, right. So that is what is referred to as a binary classifier. The specific classification model that we are going to look at is referred to as stochastic gradient descent classifier. I know there is a lot of jargon here, but we will cover stochastic gradient descent a little later in our course here. So this classifier is an example of a very simple linear model, a linear way of classification, which again we will cover a little later, right. So in order to get this class, we use scikit-learn.linear model package. Linear model module, and then the classification models also use simple fit and predict functions just like the regression models, and for now we will use accuracy as a performance metric and see how these models perform. So let us get back to our notebook. Okay. So the first thing that we have to do is to modify our target variables. So our initial target variables are all numbers, so 1, 2, 3, 4, 5 and so on. Now we need our target to be either true or false. So 5, if it is if the target is 5, then it should be 1 or true. If the target is not 5, 0. So if the target is not 5, then the value should be 0 or false, right. So that is what we do here in this first code block here. So this basically assigns a value of 1 if the target value is a 5. If it is not 5, then it assigns it as 0, right. So we do it both for the training and the test target values, right. And let us now import our stochastic gradient descent classifier here. There are a few hyperparameters. One is referred to as maximum iterations, another is tolerance, and third is random state. Random state we have defined before, right, in our regression lectures as well. Max iteration and tolerance are hyperparameters. We will take some standard values for now. In principle you need to tune these hyperparameters, right. So once you create an instance of the class, you then fit it. So fit function again takes x comma y. So x train is all our 28 by 28 pixel images, but they are basically arrays of numbers, and then the y train underscore 5 basically is our modified target value, which has ones and zeros corresponding to whether the target is actually 5 or not 5. So we have fit our model, so the model is already trained. Let us now see how good the model is. So we defined a sum digit variable here, which we saw that it was a 3. Let us see if the classification correctly classifies the sum digit as 3. So looks like it correctly classifies. So we asked our model to make a prediction on an image of 3 whether it was 5 or not, and the model has correctly made a prediction that it is not 5. Okay, so we see that the model sort of seems to work okay, relatively okay, but once again we sort of showed all the data that we had available to the model and we asked it to make a prediction. So we now need to see whether the model can do well when we do cross validation. So where we hold some portion of the training data back and then evaluate the model's performance on that held back portion of training data, and we repeat the exercise over multiple folds of data, right. So this cross validation is done over 3 fold, so this 3-fold cross validation, right, and we are measuring the cross validation score of accuracy. So the cross validation score is trying to maximize the accuracy. So accuracy is basically okay, how many, so if you show a bunch of 5s to or a bunch of images to the model, so how many predictions it gets correctly divided by the total number of predictions, right. So that is basically your accuracy. So if you think in terms of positives and negatives in the case of a classification model, how many true positives you have divided by the total number of predictions you made, right, that is your accuracy. So we our cross validation score basically tries to measure accuracy as a metric when we do this 3-fold cross validation exercise, and it has printed out the accuracy values for all the 3 models that it trained, and looks like the accuracies at least on the face of it are quite high. So they are about 95%, 96% and 96%, right. So on the face of it you may think that, oh no, these models are great, right. So you did very minimal training and it is able to do binary classification really well, it is getting more than 90% accuracy. But we also have to keep in mind that our 70,000 data points, right, are equally distributed among the 10 digits. So each digit basically, so from 0 to all the way to 9, so each digit occupies roughly 10% of the overall data set, right. So the total number of 5s that you have in your data set is actually just 10% of the entire data set, right. So about 7,000 of your 70,000 images are 5s, the rest are all not 5s, right. So if you take a random model or if your model just makes a prediction that everything is not 5, right. So it makes 70,000 predictions of not 5s, it will still have an accuracy of 90%, right. So although accuracy may appear to be a very nice metric, we see that quickly it's not very useful, right. So here we see that the model is 95% accurate, but is that accuracy actually good enough, right. So those are some things that we have to think about in classification, and we probably have to introduce other performance measurement metrics as well. So let us go back to the slides and look at and define some performance measurement metrics. So in classification models it is often useful to think of what is referred to as a confusion matrix here, right. So it has a simple sort of matrix form. So the x-axis here is the predicted class, so whether your model is predicting something to be positive or something to be negative, so something as true or false, right. And the y-axis actually defines the actual class, so what is the actual target value, whether it is true or positive or false or negative, right. So now we can have 4 types of combinations possible, right, or 4 types of predictions possible. So one is that the model is actually predicting it to be true and the actual value is also true, so we call this true positive, right. The second is the model is predicting something to be negative, the actual value is also negative, and this is referred to as true negative, right. In principle we want to maximize these predictions as much as possible, right. So true positive and true negative we want to maximize as much as possible. The third one is what is referred to as type 1 error. This is false positive, so the model is predicting something to be true, but in reality it is not true, right. So this is false positive, and you can also have the other way around, right, which is referred to as type 2 error, where the model is predicting something as negative but the actual value is positive, so this is a false negative, right. So these are the, so if you think in terms of a matrix form, these are diagonal values, these are off diagonal values, right. So you typically want to maximize your diagonal values and minimize your off diagonal values, right. That is what you want to do in a simple classification model. Now depending on how many true positives, true negatives, false positives, false negatives each model predicts, you can define multiple performance metrics, right. So there are some popular ones. So the first is accuracy, right. So this is what we saw we saw in the last few slides. So it is the total number of right predictions, so true positive and true negative divided by the total number of predictions that you make, right. But accuracy is a fairly simple metric, right. We can look at more powerful metrics, so something called precision, right. So precision basically refers to how many true positives you have with respect to all the positive predictions that your model is actually making, right. So in some cases you would want to minimize false positives, so you do not want to take up a lot of a lot of examples which you think are actually good. So you are okay with negative examples, but you are not okay with positive examples, right. We'll also look at more cases where precision becomes fairly important. So precision is one important sort of metric. There is also sensitivity here, which is often referred to as recall. So this is the total number of true positive predictions divided by the true positive and false negative kind of predictions. So here if you have high sensitivity, then you have low amounts of false negative predictions, right. And you can also define specificity, which is somewhat related to sensitivity, right. So this is true negative by true negative and false positive, negative prediction value and so on, right. So you can define a lot of performance measurement metrics if you can calculate a confusion matrix. So the confusion matrix is the origin for all of them, and we will look at precisely all the different performance metrics. So we looked at accuracy before, but we will also look at precision, sensitivity and so on, right. And the nice thing about scikit-learn is that it can generate these confusion matrices quite readily, but note that scikit-learn will often produce a transpose of this confusion matrix, right. So it will not produce this matrix in the exact form, you may have to create a transpose to get this form, okay. And how do you get the confusion matrix? So you basically use this cross validation predict from cross validation predict function from these scikit-learn model selection values. Now this is slightly different from cross validation score. So in cross validation score you only calculate the score, so the model actually does not store the actual predicted y values, predicted target values. So the cross validation predict actually stores the model's predictions. So this way you can actually calculate the confusion matrix, and once you have your predicted values, you can then use this confusion matrix function if I am not wrong, from scikit-learn metrics, right, from this module. So you can use this confusion matrix function. So let us see how to generate a confusion matrix, right. So we first create an instance of this cross validation, we first import this cross validation predict function from scikit-learn model selection, and we basically execute. So this may take a few seconds, let me execute all the 3 blocks as I keep explaining. So the cross validation predict is slightly different from cross validation score in the sense that it actually stores the y values, so it does not just store the accuracy, for example, right. So it will give us give rise to a lot of predicted values, and from those predicted values we can then calculate the confusion matrix. The syntax of the confusion matrix is fairly straightforward. The first variable or argument is your target values, and the second argument is your prediction values, right. And as you see, it gives you a nice array of numbers. The confusion matrix is once again the syntax is the transpose of what you typically find in literature. The first value is your true negative, the second value is false positive, the third value is false negative, and the fourth value is true positive, right. So if you want to visualize this in the same way as what is found in popular literature, just create a transpose of this matrix, right. So we also in case you had a perfect classification model, you will also get a perfect confusion matrix, and just to illustrate how that perfect confusion matrix will look like, we just created a pseudo confusion matrix here, right. So if you had a perfect confusion matrix, only your diagonal terms will exist, and if you sum them up, it will add up to the total number of data points you have in your training set, and your off diagonal elements will be 0, right. So that is an example of a perfect confusion matrix. Let us now go back to our slides, and we will summarize before we stop this lecture. So we looked at a simple classification problem where we wanted to predict handwritten digits in the MNIST database. We obtained the data, visualized the data, and the preparation was fairly simple and straightforward. We did fit a classification model, a simple classification model called stochastic gradient descent classification. The model by itself gave high accuracy, but we want to define other performance metrics to determine whether the model is actually good. And we started defining alternative performance metrics by defining the confusion matrix. We are not done here, we have to define more performance metrics and then evaluate how the model is actually performing, which is what we will do in our next lecture. So we will define more performance metrics, evaluate the performance of our model, and we will also look at other ways of performing classification tasks. With that, thanks again for joining this lecture. I will see you all in the next lecture.